This is the 5th lecture on advanced nonlinear physics, and it's dedicated to the nonlinear Schrödinger equation, NLS. And the form will be a bit different from the one I gave this morning. It will be simplified initially, and that let us go further in the development. So one wants to study what happens to a plane wave propagating in a nonlinear medium. And the plane wave is something like that, and it can be modulated, okay? It has an amplitude. So, and we want an equation for this amplitude function, which is called also the envelope, A of Z and T. And the total wave is, say, let's denote it as eta, why not? It's the amplitude times a carrier wave, which is of the form exponential I k naught z minus omega naught z, where omega naught, it's expressed in terms of k naught, and the relation between the two is the dispersion relation, okay? So this is the carrier wave, and this is the amplitude, and it's supposed to be slowly dependent in the sense that its typical length scale is much larger than the wavelengths 2 pi divided by k naught, okay? It's illustrated here. Okay. So if you write, if you want to account for nonlinear effect, you will write that omega is not only here as a function of k, but also it's a function of the modulus of the amplitude of the wave. And that's physical. I mean, waves with different amplitudes do not propagate at the same velocity in a nonlinear medium. In a linear medium, yes, they propagate. The propagation is not affected by amplitude, but in a nonlinear medium, amplitude matters. And it's written as omega of k naught plus a dispersion relation, which is plus the small modification. And this is a Taylor expansion around k naught. Okay, this is the first derivative, the omega divided by dk computed for k naught. This is the second derivative, but there is also a term, one makes a development around zero amplitude. So the first amplitude corrective term will be of this type. And this development is performed at k equals k naught and around a equals 0. Okay, and it's a phenomenological way. So to this usual Taylor expansion, one adds an expansion also in terms of amplitude. And I mean, this is explained more in details in the lectures. I have typed notes, which are nice, I think. And there are 3 parts. The first part explains how to do it, how to do that more rigorously than what I'm doing, but it's kind of the same idea. The second part that you may read, but not fully in great detail, is how to do it very, very carefully by using a method you will study with Caroline Knorr, which is the, how you call that, multiscale expansion. And one starts with the example in these notes of eta, which obeys KdV, and one shows that the amplitude for a behavior of this type will obey the nonlinear Schrodinger equation I read right now. And the third part in the lecture, you may discard it, it's what's happening for light in a nonlinear medium. It's kind of slightly different, but again, you end up with a nonlinear Schrodinger equation. So you should check for the notes, but otherwise, believe me, one finds that this amplitude function here, oops, so yeah, one finds that this amplitude function here obeys, which is complex, obeys an equation which is of the type by define x equals z minus and keep t. One changes the coordinate frame to go in a moving frame, which moves at velocity omega naught prime, which is the group velocity, actually. And if one does that, one sees, let me check for my notes, that A obeys an equation which is here, I A sub t, so derivative equals minus second derivative minus omega prime divided by 2, second derivative with respect to position, plus a nonlinear term, this term, where alpha is this guy, d omega divided by at k0 and at 0 amplitude. So this guy there. Okay? And this equation here, which governs the dynamics of the amplitude, it's called nonlinear Schrodinger equation, NLS equation. Right. And one wants to study the effect of nonlinearity on the plane wave. Okay, so remember the plane wave is something, the total wave is eta. So when I say that eta of zt is a good plane wave, if modulus of A equals constant. Okay, so can one find A, which is a solution of NLS, which keeps a constant modulus? And well, one can look for it, but I give you the answer. If you choose A of xt, which is an amplitude times a phase of this type, a linearly time-dependent phase, or mu is a constant. So if you insert this into NLS, you will find that A naught factorizes, the phase here also factorized, but when you derive, you would have minus mu equals 0, minus mu, right? Because I mu times I, it's minus mu, equals 0 plus alpha A0 square. So it means that A xt is just of the form A naught exponential minus I alpha A naught square t. So this is a constant amplitude solution of NLS. And if A behaves like that, you see that eta, which is here, will be a good plane wave. But this plane wave has a strange varying phase, not only this contribution there, but an additional contribution, which is triggered by nonlinearity, by this term. And this effect here, it's it's a phase shift induced by nonlinearity. And in the context of optics, when it's called self-phase modulation, SPM. And it is a known effect in nonlinear optics. Now, this is the first effect of nonlinearity on the plane wave. But one wants to check also whether or not the plane wave is a stable solution. So one wants to check, let's write A of xt, which is the one we just found, which gives, we found it a bit by chance, okay? It's a solution of the NLS, and one adds a small perturbation, okay? A small, in the sense that this guy has a modulus small compared to 1. So, and one wants to see if the plane wave is stable, if a small a will always remain small, or maybe may increase in amplitude. So that's what we will do now. And so remember, the equation is I at equals minus something like that. And A is of the form A naught exponential minus A alpha naught alpha A naught squared T times 1 plus A of xt. So for instance, when we have AT equals the same guy here times, there will be a term which is a sub t for the derivative of this guy, but also when you derive this guy, you will have minus I alpha A naught square times A. Okay, and okay, so A xx will be the sum term times A xx. That's easy. And now one has to check for alpha A naught square A. No, alpha modulus of A squared times A. So it's alpha A, which is here. Again, the same guy here. And remains modulus of A squared. So that gives A naught square. Modulus of this guy, where it's this guy times its complex conjugate. Okay. And times A, which is 1 plus small a. And the other contribution is just here. So this guy reads 1, it's easy, plus 2 ways, plus a star. This is the complex conjugate, right? Of course. And you see that, so the one we are, so okay, let's do it slowly and put everything back in the equation here. So knowing that all these guy always factorizes out. So it remains I at minus I alpha, okay, equals minus times A xx plus, so remains, what do I have wrong? Let's see, remains 1 plus 2a, and remains alpha a naught square. Okay, I want this guy to be what did I got wrong? The one here. Let me pause. Okay, I had a mistake here. I had forgotten 1 plus a, which is here. Okay, there. So here one has 1 plus a and not a. Okay, that's okay. Now, this guy cancels with this guy. Okay. Another color. One of these guy here, the 2, cancels with this guy. Because one has a, one had 2a alpha a naught square, and here one had just alpha a naught square. So it remains I at, of course, minus right to a xx plus a plus a star. So this is the linearized version of NLS. It's simple if one is not stupid enough to forget that. If you think of it, it's simple. So A is complex, and the simplest way to study this equation is to write A equals U of xt plus I V of xt, where U and V are the real and imaginary part of A. Okay, and one will write 2 equations, one for the real part of this, and the other one for the imaginary part. So, for instance, for one has A plus A star, which is T2U. Okay, and so for the real part, one has, when inserted that there, one has minus V sub t, because, okay, equals minus second derivative divided by 2 times u xx plus 2 alpha a naught square u. And for the imaginary part, one will have u sub t equals minus vxx. And that's it. So these 2 coupled linear equation can be written in a single matrix form as time derivative of, let me, there, time derivative of uv equals a matrix which is an operator times uv. So this operator, for u, it has 0 here, and here it has minus 1/2 applied on UV. And here for the time derivative of V, one has a 0 here, and here one has, let me write it, x, I change sign, minus 2 alpha n naught square. Okay, so this is the linear version of NLS written in terms of the real and imaginary part of the small perturbation. Now, it's a linear function. So one looks for plane wave solution. Okay, and the plane wave will be of that form, will be u of x, both function of x and t, will be an amplitude function. Now not function, constant amplitude, either u or v. I mean, it's complex constant, but it's constant, times exponential I, let's write it q because k is already taken, x, and in my notes I wrote minus capital omega t because small omega was already taken. And okay, so consider this equation there, okay, and look for a plane wave solution of this guy. You insert the plane wave solution in the equation there. So you will have time derivative is like minus I omega times capital U, capital V equals 0. Space derivative, it's like IQ. So this guy is Q squared divided by 2. Because I square it's minus 1. And here one will have minus Q squared divided by 2. Okay, minus 2 alpha E naught squared, 0 times U and V. Good. Let me move there. Okay, this is the equation. One will have, actually, it's a 2x2 system with two unknown functions, U and V. Okay, and this can be written as I omega minus I omega times U and V equals 0. And this type of system has non-trivial solution only if the determinant is 0. Otherwise, if the determinant is not 0, the only solution you can find is capital U equals capital V equals 0. So the determinant, which should be 0, it's simply, well, minus omega squared plus times, this is the determinant there, and it should be 0. So that gives a dispersion relation, which is omega square equals alpha a naught square q square plus square. This is the dispersion relation. So it's a bit strange. Remember, we had already a plane wave, and we look for plane wave perturbation of a plane wave, right? Well, now it's just, I mean, it's okay. It's just one needs to understand what one does. And now this guy is strange. What happens if alpha, if this quantity is negative there? Alpha times the second derivative of omega with respect to k evaluated at k naught. And I call that omega naught prime prime. So if this guy is positive, it's either because the alpha, which governs nonlinearity, is negative, or an omega 0 prime prime negative, or maybe also alpha is positive and the second derivative negative. I mean, both situations are possible. But if you do that and you plot, say, omega square plotted as a function of, let's say for simplicity, q square. So it's easy. This contribution here is dominant at small q square, and it's a linear contribution. It's and with a negative slope, something like that. And then a large q square, this guy dominates. So you have something like that. Okay. And for all this range of k there, for all these k's there, you have omega square, which is negative. And that's bad news, because if omega square is negative, it means that you can find omega, but it's imaginary. So here you have of the omega equals plus or minus I times something. And this something will be, say, positive. I put the plus or minus here. But remember, we had in the wave a behavior which was minus I omega t in plane wave analysis of the small perturbation A. Okay, A of xt has a contribution, something like that, which is here exponential minus I that makes plus or minus something positive times t. So the plus diverges exponentially rapidly. One speaks of the wave is unstable. One speaks of dynamical instability. And it's called also, and this dynamical instability is triggered by omega, which is negative at large wavelengths, small q, and it's called modulational instability in this case. But never mind. So, so what will happen is that, well, first, what is the most unstable mode? And that's in here, this here, where this q star, where q star square leads to the most negative omega square, means omega, which has the largest imaginary part, which is the one which diverges more rapidly. Okay, so let's determine this q star square. So one has omega square. Oops, no, it's not well. A bit. One has omega square, which is alpha x, where x is q naught square, plus, I think it's by 2 x square. Okay, so one has d omega square dx equals 0 when alpha plus x equals 0. Okay, it means that it is q star square, which is x, equals minus, oops, sorry, yeah, it's a square. And here I have a 2 here. Add a 4. The 4 is killed by the derivation and remains a 2. And it means minus 2 alpha I0 square divided by, okay. Let me check with my notes. It's if it's correct. It is. Okay, so this is the most unstable mode. It means that I will have something like that. I start with my good plane wave here, which is eta. This is the carrier, remember? And then for later time, if I have not something which is not exactly perfect, a small perturbation will increase in time, mostly with this wavelength. So one will have something like that. Let me try to do it properly. Here, when we have a modulation, with amplitude will increase, and here the wavelength will be 2 pi divided by, and this is z, 2 pi divided by q star. Okay, so if one performs a Fourier transform of this function, one will have initially, so the plane wave initially, if one makes a Fourier transform, it will have as a function of k, it will be centered around k naught, okay, something like that, at t equals 0. But for later time, if one performs a Fourier transform, a special Fourier transform at later time, one will have something which still the center peak around k naught. But now, 2 new peaks will tend to develop at k naught plus q star. And of course, q star was defined by its square, remember? And also one has q naught minus q star there. And these are called side bands. Side bands. And they are populated because of nonlinearity, populated because of nonlinearity. And this is what is observed. If you check in the notes, I can comment on that. I just show you the picture, sorry. This is there from the handwritten, from the typed note. So this is an experiment. People were sending a laser in a nonlinear medium, unstable nonlinear medium. And you see this there is the initial laser, or more specifically, they look at the output and they increase the intensity of the laser. So small intensity, plane wave, then this is the Fourier transform of the signal. Plane wave remains plane wave. Intensity increases a little bit more, and even more. One sees the two sidebands which develop. And even the sidebands themselves have new sidebands because, of course, I mean, that goes forever. So this is an illustration on how, because of nonlinearity, the plane wave can be unstable. This was first, this instability was first predicted and measured for linear water waves by Benjamin and Fear in the 60s. And this is something much more recent. You see a PRL of 86. So that's it for this lecture. My advice is that you go through the typed notes, especially section 1, which is a clear derivation, or clear, a clean, more or less clean derivation of this equation there. Section 2 and 3 are also derivation more mathematically grounded, but maybe a bit difficult. And section 4 is really what I just did here online. This is the end of this lecture.